Hi, my name is Ebuka Nkor, and today I'll be discussing Megan, a resource aware prompt injection defense for cybersecurity LLMs. So, this is going to be the outline, introduction, the problem statement, the related literature, the method we used in this work, the preliminary results, and then conclusion. In introduction, I want to start first by saying that LLMs have gained very wide applications in different domains. But in cybersecurity, there is a three focused area for intrusion detection systems. Example is like NVIDIA Morpheus. The second is for Security Operations Center. It actually like helps the security experts reduce the time to analyze many incident logs or operations. And then the third is malware analysis. So LLMs can analyze large context and content of data, and then make predictions. However, there is a serious problem with LLMs, which are prone to prompt injection attacks. So prompt injection attacks, or PIAs, are a class of attacks within cybersecurity LLMs. The goal of the attacker here is X sub C, which is to use a target data, that's X sub T, concatenated with Z, a prompt, which is X sub E. So when the target data is mixed very intelligently or concatenated very intelligently with a prompt, then an adversarial construction of the LLM is achieved, and this has severe consequences. The consequences of these PIAs and cybersecurity LLMs themselves are in misclassification of malicious code, bypassing threat detection, corrupt attack mapping, and generation of false reports. And this becomes a very serious problem case for LLMs that are being used for cybersecurity domains. So there are different benchmark methods to prevent against or to defend against these PIAs. The first is the preventive method, and the second is the defensive method. The benchmark defense methods against PIAs are the heuristic methods. These heuristic methods talk about the use of strings on characters, to prevent or to defend the model against prompt injection attacks, while the optimization methods use maybe another model or another defense model or optimization techniques to defend against prompt injection attacks. So the problem statement here is that we want to ask and find out if heuristic recursive prompts trigger denial of service within security LLMs. The second one is, what impact do LLM delays have on real-time intrusion detection? And then the third is, do existing defense address resource exhaustion attacks? So we find, or we try to see a situation here where um, the attacker poisons the data, which is like the poison data, into the training data set of the LLM. And so the detection LLM or the model itself is being poisoned. And then the aftermath effect is that there is delayed detection, expanded evasion window, longer time response, and exhaustive CPU and GPU resource. And for the prompt output model, the LLM keeps checking or delays malicious alerts endlessly, and then misses an alert system, and then the attack itself is successful. This is the goal of the attacker, to use this poison data to infiltrate the training data set and then corrupt the large language model itself to have like some of these unexpected unplanned like cases. And so some works here have also done some foundational defense methods against this kind of prompt injection attacks. So for these ones, these authors use chain of thoughts, to defend against prompt injection attacks, and their application area is in general purpose. Uh, And then the next one is they use spotlighting method. They use like delimiters. These are heuristic methods that spotlight sequences of tokens. So there are specific tokens within a particular um, sequences of text, and then based on those spotlights, it gives them severity, uh, concentration, or spotlights, and then they are used to semantically design the output to know if it's like going to be vulnerable or not. And then model fine tuning. These authors just discussed, they did not have like any contribution. And then ML based methods, they use like classifiers to detect recursive attacks. And our proposed method here, unlike all these authors, is that they do not consider the fact that a particular prompt can be recursive, and the recursive nature of that prompt can cost a cybersecurity LLM detection abilities. And other authors just focus on semantic safety, but we also do the same but with addition to computational resilience. And so we use like a delimiter based defense method, you know and other like heuristic methods to design a resource aware prompt injection attack defense method, Megan. So these are methodology which I just want to go through briefly. In this work, we do not use like a general or generalistic LLM. We use a cybersecurity LLM, CySec, found on Hugging Face, and then we craft our own data set, which is to poison the LLM itself and see the output that it gives when in three conditions: before poisoning, during poisoning, and after poisoning. So these recursive prompt injection attacks are evaluated within these three scenarios. And then we measure like the inference time before poisoning, the token count before poisoning, the detection delay before poisoning, and the same as well during poisoning and after poisoning, as shown in this diagram. And then the results are presented in this slide. So we see that for the average time for the benign or the normal LLM is 6.18 seconds, but after poisoning it becomes 46.69 seconds, and during the defense design the average time reduces, and then the tokens as well also vary in the same vein. And then the detection rate is 100% before and also 100% after, but during poisoning is 0, because the prompt injection works, and it's also like consumes a lot of time. So this is what an attacker can actually do, and this is what we have done. But now defense, we try to defend the LLM against such poisoning attacks. And then we use the KL divergence score to measure the difference or like the score or the weight of the benign and attack distributions. And also we measure this figure here is also like just like a duplicate of what we have before. We see like the computational latency represented in figures, the output volume explosion in tokens, and then we see here that the bar in red is the computational latency, while the bar in green is the baseline, and then the defended method Megan is in blue. And we see within the computational latency, the output volume explosion, and then the security effectiveness, our model is effective, or like our design is effective against like the the expected prompt injection. So the key insight here is that there is 7.6 times latency increase under an attack, under a prompt injection attack, and then token explosions as well, which consume carbon footprints for the LLM. And the key insight with our defense is that we reduce the latency, reduce token explosion, and then 100% defense restoration. So, in conclusion, we conclude by saying that cybersecurity LLMs are prone to prompt injection attacks, and it's been verified in our experiments. Also, the recursive nature of those prompt injection attacks are expensive and devastating for cybersecurity LLMs. And the third one is that our proposed method, Megan, which means defense or strong security, propose a resource-aware defense against PIA attacks in cybersecurity LLMs. So our next step is to explore with other benchmark LLMs, because in this study we used only the we use only the um, we use only the Zyzek LLM, but we want to explore with other LLMs as well, and then various experiments for maybe different iterations or numbers or recursive settings, and then compare and test experiments with benchmark LLM studies if possible. Thank you.